Hello and welcome to another video on kinetics of rigid bodies. So let's consider this question. The question says the rack arrow of the rack and piston is moving upwards with a constant velocity of 10 foot per second. What is the angular velocity and angular acceleration of the bar BC? Okay, so as always, let us take a pictorial view of the diagram, a sketch of the diagram, and explain. Now you're given a rack and piston system. This is a rack, and from the question, the rack is moving upwards. Okay, this rack is moving upwards with a velocity of 10 foot per second. All right, so let's analyze this motion now. If this rack is moving upwards, that means this gear is compelled to move anti-clockwise. Okay, if the rack is moving upwards, it means the gear is compelled to move anti-clockwise in this direction. So we'll have something like this. The gear is moving in this direction. Observe that point D is fixed in the gear. Okay, so if it is moving in this direction, so it simply means it is moving in the anti-clockwise direction. Okay, so keeping that in mind, I've said whenever you're analyzing motion of rigid bodies, you always consider the points that are fixed. Now, since point D is fixed, this simply means that the velocity at point D is 0, and therefore the relative motion between D and C is going to now be what? The same motion as the motion of the rack. Okay, so the speed along DC is going to be equal to velocity at velocity of the rack, which is 10 inch per second. But let's explain this. Let's pick out the fixed point. So consider the motion or pure rotation of point D. Since point D is fixed, we consider the pure rotation of point D. All right, so now we consider the pure rotation of point D. Okay, so this is point D inside the gear, so which means point D is actually fixed. And if point D is fixed, it means that the velocity at point D automatically is 0. So Vd is equal to 0. All right, so let's simply use this to indicate okay, being fixed. Let's just all right, to show that point D is actually fixed. Now, we said that since the rack system is moving upwards, okay, since the rack system is moving upward, it means this gear will rotate anti-clockwise. So, which means motion along CD is actually in an anti-clockwise motion. The angular speed is simply angular or omega dc from D down to point C. Okay, so keeping this, remember I said once you have your angular speed, then you're going to have, in the previous videos I explained this, that once you have your angular speed at the other edge of the bar, you're going to have your linear speed, which is the relative speed between point D to point C. And that speed must always be at 90 degrees and in the same direction of motion. So it must be in the same direction, anti-clockwise, then it must be at 90 degrees to the arm. So you have something like this at 90 degrees to that arm. All right, so this is our velocity from D to C, which is relative velocity from D down to C. Okay, and I said that this relative velocity VDC is given simply as VC minus VD, which means the velocity at the free end minus velocity at the fixed end. Okay, all right, so the aim now is to find velocity at point C. So we simply make VC subject of the formula. This simply implies that velocity at point C becomes, sending VD over here, we simply have VDC plus VD. All right, so we have this to be the equation of velocity at point C. But not forgetting that velocity at point D is fixed, so it doesn't have any velocity, therefore Vd is 0. And if Vd is 0, this simply implies, putting that into this equation, that Vc is actually what? Vdc. All right, so our velocity at point C is equal to or similar to the relative velocity between point D and point C. What now is the relative velocity between point D and point C? All right, so observe that from the question, it was stated that the rack is moving upwards with a speed of 10 foot per second. As this rack moves upwards, the gear also moves in this direction, clockwise, anti-clockwise direction. Now the gear moves at the same speed as the rack. Okay, the higher the speed of the rack, the higher the speed of the gear. So which means the gear moves at the same speed as the rack, and that simply means the motion along D to C is also the same motion as the motion of the gear. So this simply implies that velocity along D to C, which is velocity along this arm, is equal to the velocity of the gear, which is equal to the velocity of what? The rack. So that simply remains what? 10 foot per second. So this simply means that the velocity, okay, between C to D is simply equal to 10 foot per second. And if that's the case, putting that into this equation, therefore, we obtain that the velocity at point C also remains 10 foot per second. So this is the velocity at point C. Okay, whenever you're analyzing motion of rigid bodies, always start from the fixed point. So looking at the diagram again once more, another fixed point we have here is point A. Point A is fixed, so we simply consider pure rotation. Since it is fixed, it exhibits pure rotation. But now, where is the direction of this rotation? Observe that if this arm is moving, or if the angular speed of D to C is moving anti-clockwise, that will make the angular speed of this motion from C down to B to move clockwise. So this object will move in the clockwise direction. So this is angular or omega C B, from C down to B. Okay, so it moves in the clockwise direction. And if this is moving clockwise direction, it means that this arm will move in the anti-clockwise direction. So this is omega A B. All right, so it means that the motion of point A will move in the anti-clockwise direction. So now you consider pure rotation. Since point A is fixed, it means it cannot move. It can only exhibit what is called pure rotation. So we consider the pure rotation of point A. Draw out the free body diagram of arm A to B. Then recall that if the motion of point A is moving in the anti-clockwise direction, remember we said on the other free end there's bound to be a velocity which also moves in the direction of motion, and this velocity must be at 90 degrees towards the arm. So arm AB is this. Now we are going to have a velocity which moves at 90 degrees in the same direction as direction of motion. So at 90 degrees to this surface, you have something like this. Okay, so this is our velocity v VA relative to B. So relative motion from A down to B, and it must be at 90 degrees to this surface as can be seen. Okay, so let's pick out the free body diagram of arm AB and consider the pure rotation of that arm. All right, so now we consider the pure rotation of A, which is A to B. Okay, so remember the motion is anti-clockwise. You have something like this, omega AB, and of course you have a speed which acts at 90 degrees at the free end, and it must be in the direction of motion. So this is called VA relative to B, and you have this. Okay, now remember that the relative speed VA to B means the velocity at the free end VB minus velocity at the fixed end VA. Okay, so the aim is to find velocity at the free end, which is VB. Therefore, VB is equal to VA to B. Now, this negative sign cross an equal sign becomes positive, so I have plus VA. But since point A is fixed, this implies that VA is equal to 0, and this simply means that the velocity at point B is equal to the relative velocity between A and B. Okay, so VA So this becomes the value of the velocity at point B. What then is the relative velocity of A to B? Remember, VA to B is equal to the position of AB, which is the radius arm, multiplied by the angular speed of AB. You have this. So, which means we need to find the radius arm of distance from point A down to point B needs to be found. Now, let's take a look at the diagram once again. This is our diagram, and we don't know distance from A to B, but we are given sufficient information to find that distance. Once more, we are given this height, which is from here to here was given as 12 meters. you were also given this distance from here to this point was given as 6 meters. So we can simply employ the right angle triangle rule to solve that. Okay, so let's do it quickly here and see. So you have this, and you have this. This distance was given as 6 meters. The height was given as 12 meters, and we need the radius A to B. So we simply employ Pythagoras theorem. All right, so AB all squared is equal to 6 all squared plus 12 all squared. So AB all squared is equal. So I'm going to be punching this all together. So I have 6 squared plus 12 squared. So that simply gives me 180. So we simply find AB to be the square root of 180. Okay, so we obtain the square root of 180, and square root of 180 simply gives us AB to be equal to, that gives us approximately 13 meters. So AB is simply 13 meters. All right, so having that distance in mind, it means this RAB, okay, RAB equals 13 meters. So we know the position or distance between A to B. Now we can find the relative speed. Therefore, VAB equals RAB, which is 13 meters, multiplies angular speed relative to B from A. All right, so we have this. This simply implies that VAB is equal to 13 omega AB. All right, so keeping this aside, but not forgetting earlier we said that the velocity at point B is equal to the relative velocity between A to B. Now, this simply means, okay, this simply implies that velocity at B is equal to 13 omega AB. You keep this velocity aside. So that is the whole analysis of A to B. Now let's fall back to the diagram. So in the previous video, I explained that if this arm is under rotation and this arm is also under pure rotation, which means they are fixed, then the arm in between is not fixed. Since it is not fixed and it is connected in between two fixed arms, it means that arm B to C is undergoing what is called the general plane motion, which is combination of both rotation and translational. Since these two arms are fixed, it means from B to C is undergoing translational motion and it is also undergoing rotational motion at the same time. So the motion of arm BC is simply called general plane motion. Now we consider the general plane motion of arm B to C. That's the next thing to do. Consider the general plane motion of arm B to C. So we are simply going to pull out this diagram as explained in the previous video, and then we are going to be drawing two separate diagrams of it, one for the translational and the other for the rotational. And remember, I said in the previous video, when translating, you translate about the known velocity. So recall we analyzed earlier and we found out that the velocity at point C is still the same thing as the velocity of the rack. So we said VC is equal to 10 foot per second. Okay. So we said velocity at point C equals 10 foot per second. Okay, so you translate about the known velocity. Since velocity at point C is known, it means we are going to be translating at point C, also rotate with the known velocity. So we also rotate about point C. Okay, so let's do a free body diagram of the general plane motion of that arm. So considering the general plane motion of arm BC, this is what we have. Remember, here is B and here is C. And then again, not forgetting that we obtained, since A is rotating in this direction, we had the velocity at point B, which was at 90 degrees to this arm A to B. So observe also the direction or the inclination of that velocity with this arm BC. So we're going to use a straight line or an inclined line over here just to indicate portion B to C. Okay, so we can accurately get the direction of 90 degrees and its inclination on portion BC. So VB is at 90 degrees to this arm AB. So you have our VB to be this. All right, so this is 90 degrees to AB. So this is VB, and we got VB, not forgetting, let's also pull it out. And not forgetting, we got VB to be 13 omega AB, which is velocity at point B. Okay, so let's pull it back to the diagram now. So VB, we obtain it to be 13 omega AB, and you have this. Okay, now the known velocity is at point C, which is 10 foot per second. So the first diagram is diagram of translation. So we are translating the known velocity, translational motion plus rotational, which is general plane motion, plus rotational motion. So the first is translational and the second is rotational. Not forgetting here is B and here is portion C. Okay, so we translate with the known velocity. Velocity known is at portion C, which is 10 foot. And again, when translating, it must be in the direction of motion of the arm. So since the arm is in this manner, translation will also be in that manner. So your translational velocity becomes this. So you have this known velocity. You also have this known velocity. Okay, and this is going to be 10 foot per second. Okay, 10 foot per second, which is also 10 foot per second. Okay, that's the known velocity. Similarly, you rotate now. Remember, here is also point B and here is point C. So you also rotate about the known velocity. Since velocity at point C is known, then you fix this region. Fixing here, then you turn here about. Okay, turn here with a speed. So simply call that speed omega CB relative to B. So this becomes angular speed CB, and you have this. Now remember I said once you fix a point, then the free end will have a relative velocity from C to B, which is linear, and it is at 90 degrees to this arm and must be in the direction of motion. So 90 degrees is somewhat here. This is 90 degrees and it must be in the same direction as direction you assume. So this is our velocity. Okay, so you call this VCB, which is velocity from point C relative to B, and you have this. Okay, so having done with this, the next thing to do now is you draw the vector diagram of the velocities. Okay, draw the vector diagram of the velocities. Observe the direction of the CB. Okay, so its velocity, which is the translational velocity, is in this manner. So this is your translation. So I'm going to pull up the original diagram now just to explain this direction. This might not be properly drawn, but then I'll just show the clips of the real diagram so you see the direction of B to C. Okay, all right, so which means it's somewhat in this manner. This is my translational velocity. So this is V, this is VC. Okay, that's VC, which is a known velocity. Not forgetting that the um, the relative velocity is at 90 degrees to that surface. So at 90 degrees, we have to this same translational velocity, you have something like this. This is at 90 degrees to this surface. So you have this. So this is our relative speed. So this is VCB. Now the line that joins them together, of course, is this velocity at B. As can be seen, the velocity here is inclined at an angle. So the line that joins them together is simply this velocity at point B. So you have this joining vector from here to this point. So this is the velocity that joins them together. That is simply velocity at point B. Okay, you have that to be velocity at point B. All right. All right, so we need to now find the angle between either of them. All right, so to do this, I'm going to be showing once more the original diagram, okay, because my diagram is not properly drawn. So I'm going to be showing the original diagram. Okay, now, so we have B to C, and this height was given as 12 meters whereas this height was given as 10 meters. Okay, this is 12 meters. So this simply means that if I draw an imaginary line from here to this point, okay, let's say I draw imaginary lines or broken lines, okay, from here to this point, it simply means that if from here to here is 10 and from here to here is 12, it means this height alone, let's just call here point D or simply call here point O. It means this height from B to O is simply what? 2 meters. It means that height is simply 2 meters. So this will help us to find the angle of the incline, all right, between C to B. So let's simply call this angle theta. Now we need to find that angle. Knowing that this base from O to C is 16 meters and this height is 2 meters, we can be able to find that angle. Okay, so tan theta is simply opposite all over adjacent. So we have that tan theta equals opposite. The opposite arm is 2. So you have 2 all over adjacent is 16. Okay, all over adjacent, which is 16. So this means that the angle theta, of course, is found by taking the arctan of 2 all over 16. So theta is equal to, now let's find the arctan of 2 over 16. So arctan of 2 over 16 simply gives us 7 degrees. So it means the angle from B to C or C to B is 7 degrees. Not forgetting this is the hypotenuse arm and this is the horizontal line. So the angle between the hypotenuse arm and the horizontal line is given as 7 degrees. So let's trace that now on our velocity vector diagram. Okay, so not forgetting this is the hypotenuse arm and of course this is the horizontal arm. The angle between the two of them is taken as 7 degrees and you have this. Okay, now if that is the angle, then we can now solve in terms of the known velocity. Remember, we are asked to find the angular speed of B to C and also the angular acceleration of B to C. So there's no need now to find the value of the velocity at point B. So let's go straight to find the velocity of what? VCB, which is VCB, velocity at C relative to B. Alright, since we are looking for the relative angular speed between C to B, then we'll simply look for the velocity at CB. Now relating this to what? Velocity at point C, which is a known velocity. Okay, so remember tan 7 is opposite all over adjacent. So we simply employ tan 7 equals opposite is the relative speed, which is VCB all over adjacent, and adjacent is VC. Alright, so we make VCB subject. This simply implies that VCB, okay, is equal to VC tan 7. Alright, so not forgetting that VC was given as 10 foot, and this simply implies that the relative speed VCB is now going to be 10 foot multiplied by tan 7. Okay, so this simply implies that VCB is going to now be equal to, so let's obtain 10 multiplied times 7. That simply gives us 1.25 foot. So it means that the velocity foot per second, so the relative velocity between C to B is simply given as 1.25 foot per second. So if we know this to be the velocity, then we can find the angular speed. Angular speed of CB is going to now be velocity of CB multiplied by the radius arm of CB, and this is equal to velocity of CB. We obtain that to be 1.25 now multiplied by the radius arm, which is distance between portion C to portion B. So the radius arm of portion B to C is total distance from B to C, which was given us here as 16 meters. So simply multiply this value by 16. Okay, so this implies that the angular speed along CB is going to now be equal to, okay, so find 1.25 times 16, and that simply gives us 20 radians per second. So this is the angular speed along portion BC, 20 radians per second. Okay, so having found the angular speed, the next question says we should find the angular acceleration of that arm. Now, the angular acceleration or the angular acceleration at portion C is given as the angular acceleration along CB, okay, times the radius arm of CB, all right, minus the angular speed of CB all squared multiplied by the radius arm of CB. All right, now this is the formula, but at point C, we weren't given any angular acceleration. At point C, no angular acceleration was given, so which means angular acceleration at C is equal to 0. And if that's the case, then if you put here as 0, remember the radius arms will cancel out. That simply gives us the angular acceleration of portion AB, and this implies that the angular acceleration of portion CB, sorry, not AB, of portion CB will simply be the angular speed of portion CB all squared. Okay, so this is equal to, we have 20, which is the angular speed of portion CB, all squared. All right, so this simply implies that the angular acceleration of portion CB is going to now be equal to, let's obtain 20 squared, that gives us 400 radians per second. Radians per second squared. So this is the value of the angular acceleration of that particular arm CB. All right, guys, so that's it on this question on kinetics of rigid body. In the next video, I will see you with another question. Thanks and cheers.